Hi everybody, this is Mrs. Ellsworth. In this video we'll be talking about speed, velocity, and acceleration. We'll be looking at graphs and we'll also be looking at the formulas that we need to use to solve problems involving speed, velocity, and acceleration. First, let's look at just speed. Okay, speed is the ratio of distance an object moves in a certain amount of time. In physics, we quite often have these definitions and we write them into formulas. So if you really look at this, the average speed equals the distance an object moves during a time period. So the average speed we're talking about, like if we would go up to Duluth. We would drive up to Duluth, it's a certain distance divided by the certain time, and we would get the average speed. Let's look at our formulas. Here is the velocity equals distance divided by time. But we have talked previously also about displacement. So this could also be speed equals the displacement divided by time. You can choose either one of these formulas and they are used exactly the same in most situations unless you're not starting at a zero spot, and then you would want to use displacement. But for this video we will be using distance. Okay, let's go ahead and move ahead to slide 15 in your notes so we can look at the formulas and how to manipulate them. Okay, here is our two formulas that we're talking about. They are identical formulas, just that this one is distance and this one is time. And here is if we're going to solve them for distance or displacement. I went and manipulated it around, so this is a formula page that we'll use, and later on you'll want to go and change these formulas and put them onto a resource page that you get to use on your tests. So make sure that you keep this section handy. Let's also solve these different formulas for time. Okay, so here is the time equals distance divided by velocity. I know that several of you are also thinking, well, gee, I know how to use this formula. I'll go and insert my values in for the certain ones and solve for time, and that's fine. Some students are very confident in math and they can do that, but they find overwhelmingly that statistics show that if students go and manipulate the formulas first, that they will have more success. There's a higher success rate with those who manipulate the formulas first. Again, this is one formula. Here's another one replacing the displacement. Changing the distance with displacement. Okay, let's go back to our slide. Okay, so let's go ahead and look at what type of units that we would have. Okay, distance is often measured in meters, kilometers, and centimeters. Okay, and the time would be often in seconds, minutes, or hours. And it could be any variation of however you chose to do it, but here's some common ones. Now, speed will be taking this and dividing with that one, so whichever ones that you choose, that will be your unit for speed. So some common ones that you might use for distance would be meters, and then the seconds, so be meters per second would be your average speed, or centimeters per minute if you've got something going slow. Kilometers per hour is what we would typically measure like in a car. And so those are some common units that we use for speed. Now I want you to know that this is a velocity formula also, and so we will be talking about that one later on. Okay, let's look at speed and velocity in a graph. We've talked about this one briefly where I was walking in front of the classroom and showing a certain rates and stuff like that, but think about it. What does the slope equal? You know that slope equals rise over run. Well, rise is the distance in this case, and the run is time. I don't know if I like this too much with this. I should have had a different slide there, but anyway, so distance versus time, so it'd be distance over time, which could be, in this case, meters per second. But what does that really equal? That equals the velocity or the speed. Okay, so the slope in this will always, on a distance time graph or a position time graph, they're also called too, a position time graph, they are quite often used to help determine the speed by finding the slope. Okay, looking at this graph, you'll notice that in 10 seconds they go from 0 meters to 60 meters. So that slope right there, we could determine that the speed of it, so it'd be 60 meters in 10 seconds, and so 6 meters per second. Here they're stopping. They're staying at 60 meters, staying at 60 meters for 5 seconds, and then they go right back to where they started from at the 0 point. And if I had a meter there, we'd be walking behind the meter, so we couldn't detect it, but here we go. We keep on going back beyond their starting point. And so we go there until 40 seconds, and then we bounce off at that point, and then we go right back to where we started from. Remember, we talked about displacement. The total displacement in this one would be none. There wouldn't be any displacement because they hadn't moved anywhere after, from start to finish. They're in the same exact spot. Now, their distance would be quite great. You could add up all the distances and get the distance. Okay, let's talk about velocity this time. Okay, velocity uses the same exact formula that we had before, but with velocity we've got one more thing involved in it, and that, oh, hold on, same exact formulas, okay, but we've got one more addition to this. Velocity is speed also, and it's also direction. So when we're talking about velocity, we've got to include more in our problems and more in our answers. So let's just look at a speed problem. Callie rode a bike 6.2 kilometers in a half hour. What was her speed? So we're looking for speed, so we'll use our formulas. For this case, I'm just going to use the distance formula. Okay, and we went 6.2 kilometers in a half hour, so 0.5 hours. So once you go and divide that with your calculator, 6.2 divided by 0.5, you'll go and get 12.4. And look at our units already calculated for us. This was kilometers over hours, so we get kilometers over hours here too. So that's great. It calculates even your unit. Okay, here's another one. Devin drove a remote control car south 230 meters, and he did that in 50 seconds. Let's go back and look at our formulas again. Okay, we're looking for velocity, so it'll have to be either this formula or this formula. When you're looking for velocity or speed, you look for, well, what is the variable that they're looking for? It needs to be a v equals in this case because you're looking for speed, or else you're looking for velocity. Okay, what is a speed? So we'll use this formula. Okay, and we'll find the distance, which is 230 meters. And then the time is 50 seconds. And we'll go and divide that 230 divided by 50, and we'll get 4.6, and then our units are already there for us. They're meters per second. That's great. So our answer for the speed is 4.6 meters per second. We watched a video that talked about how that this is a scalar unit, and that scalar units is basically just, or a scalar quantity, is basically just a number and a unit. But velocity is not scalar. It is a vector. So we'll go and calculate it too. Okay, same exact formula, so I mean, it's just why we calculate it is speed, plus it is also direction. And this one gives a direction as being south. So it is 4.6 meters per second south. And you have to include both of those in your answer for velocity. So when I ask for speed and velocity, velocity's just got one more part to its answer. Okay, now let's look at acceleration. Acceleration is a change in velocity over a period of time. And we show our formula to be like this, where it's showing a change in velocity, which we go and take the final velocity minus the initial velocity, and we divide it by time. What is the final velocity? That's the speed that you're going at the end of the problem. And the initial velocity is the speed that you were going at the beginning of the problem. Do you need to write that down in your notes right now? Anyway, let's go ahead and look at the units. Okay, the units for the speed or the velocity we've already talked about. They could be meters per second, they could be kilometers per hour, they could be centimeters per second. But the time period in this one is a little bit more fussy. If you're going to use meters per second, you're going to have seconds for your time period. If you're going to have kilometers per hour, we're going to have hours in our time period. If we're going to have centimeters per second, again, you'd have to have seconds. But these could be any type of units, not just these ones. And these are the typical time period ones that we use. Anyway, so those units is what we would use to calculate what our acceleration unit is. If we had meters per second over seconds, it'd be meters per second per second. We do go and clean that up and we write it as meters per second squared. Sometimes students will see this unit in a problem and then they will think that they need to square some type of value. No, this is the unit for acceleration. If we had kilometers per hour as our velocity, and then we would have to have hours as our time unit too. So we'd have kilometers per hour for velocity divided by more hours, kilometers per hour, or kilometers per hour squared. Okay, and then those are our typical units that we use for acceleration. Okay, let's go ahead and look at a problem involving acceleration. Claire was passing a tractor. She started at 55 kilometers per hour, then she accelerated up to 95 kilometers per hour. That's not even 60 miles per hour. All in 20 seconds. Find the acceleration. I do see a problem. We've got hours and we've got seconds here, so we're going to have to do some unit conversion before we're done with this problem. Okay, let's go check out our formulas. Okay, if we're talking about all of the different acceleration formulas, we've got to go and figure out how can we manipulate them, and I've done that for you. So you can go and use this, write down all the formulas, and then you can also later on go and put these on your resource sheet that you get to use on the test. All the acceleration formulas right here in maroon, all solving for one of the different variables. Okay, so here is the one that we need because we're looking for acceleration, so you need to find acceleration equals formula. Okay, and then we will go back to the problem. Okay, here's our formula that we're going to use. Now we need to figure out what are all of our variables. So when you look at this, you'll notice that we need a final velocity. She accelerated from 50 kilometers per hour to 95 kilometers per hour. So the final one would be the 95 is towards the end of this problem. Okay, and then so we'll go put down 95 kilometers per hour. Now let's go and find that initial velocity, which is the one that happened first in the story, which would be the 50 kilometers per hour. Okay, so we'll insert that into our formula, 50 kilometers per hour. Now we just need to know the time period. And the time period you'll notice is 20 seconds, but we have a problem here because we have got hours in our formula, already, and so we need to do some conversion. And here's a simple way for converting. You know that there is 60 seconds in a minute and 60 minutes in an hour, so I kind of took 60 times 60, and I got 1 hour equals 3,600 seconds. So I'll go and I'll take my 20 seconds and well, I suppose we should cancel out our units first. 20, remember fractions, you multiply across the top, we'll get 20 over 3,600, and so when we stick that in our calculator, we'll get 0.0056, well actually it's 5 repeating, hours. So now let's go and insert this into our formula. Okay, there it is. So now you quickly just put in your calculator, pretend that the numerator, if you're going to stick it in your calculator straight up, either you need to calculate your numerator and press equals, or else you need to put parentheses around that numerator and then divide by the 0.0056. And when you do that, you're going to get 8,036 kilometers per hour squared. Remember, also just one little thing that in metric we do not write commas in our large numbers. Okay, so that's how we can solve for acceleration. I hope that you wrote every step down so that it'll save you time when you're going to go and do these problems in our problems worksheets. Okay, now we're going to skip ahead to slide 16. Okay, I wanted to show you what a velocity time graph is. A velocity time graph, when you think about velocity divided by time, you're talking about acceleration. So this really shows acceleration, the slope does. But think about it. You're going from 6 meters per second to 12 meters per second, and you did that all in a period of 4 seconds. So this is showing a constant change in speed or a constant acceleration. Now at this point of this velocity time graph, remember it's velocity time, it is not a position time graph. Now they're going at a constant speed of 12 meters per second, 12 meters per second in a velocity time graph, and then now they're going to slow down quickly to where they're at 0 meters per second. This is not a position time graph, so they were never stopped. This is what their speeds were changing as time went on. In fact, if you go and look at this one, this one shows a constant change in speed. This is a distance time graph or a position time graph. It shows a change in speed. When it's that nice of a distance time graph, you do get a velocity time graph that has got a straight linear line on it. Okay, what is instantaneous acceleration? Well, that is acceleration at one moment during time. So when Claire was passing that tractor, at any second we could have checked her acceleration at that instant, and that would have been her instantaneous acceleration. Okay, Now we're going to skip that one. We're going to talk about negative acceleration, which is also called deceleration.